Hi, my name is Manish Gupta, and in this video, I'm going to talk about robustness of fine-tuned transformer-based NLP models. This paper has been accepted at EMNLP Findings 2023. This work is in collaboration with Pawan, Subba, Monica, Venkateshwar Rao, and myself. This is a very interesting collaboration. Pawan is from NIT Warangal and Professor Venkateshwar Rao again from NIT Warangal. Subba is from India. Monica was at IIIT Hyderabad when this work was done. Now she is at University of Bonn. Let's get started. Okay. So there are some interesting questions about transformer-based models that we try to answer in this work, specifically about BERT, GPT-2, and T5. When you use these models, you of course fine-tune them for various tasks. And when you fine-tune them for downstream tasks, they modify the representations generated by each layer. So while fine-tuning these models, an interesting question is that what changes across layers with respect to the pre-trained checkpoints? Which layers see a lot of change, right? And then the other questions are around robustness to input perturbations. So when you provide input, clean input without any adversarial perturbations and so on, these models, of course, give very good results. However, how robust are these models, BERT, GPT-2, T5, to input perturbations? Is the effect of fine-tuning consistent across all the models for various NLP tasks, or is it different? Do these models exhibit varying levels of robustness to input text perturbations when fine-tuned for different NLP tasks? So all of these are interesting questions that I'm going to talk about in this video. So let's talk about how do you compute similarity between representations learned by different layers between two models. So essentially you have a pre-trained model and you have a fine-tuned model, and you want to sort of compare what changed. Now to compare what changed, it's important to define a representation similarity analysis, right? So if you look at the outputs of various hidden layers in these two models, the pre-trained model and the fine-tuned model, you can compare the outputs. How do you compare those outputs? Well, two of these metrics have become popular recently in the literature. One of them is called CKA, the other is called STIR. Okay, so let's basically talk about these two metrics, at least broadly try to understand what they try to capture. Okay. So what is CKA? Well, CKA is used to compare layer-wise hidden state representations of pre-trained and fine-tuned models. So in this work, we basically use 12-layer models. So therefore, we basically have like 13 different layers, right? CKA basically tries to compare layer-wise hidden state representations of this pre-trained model and the fine-tuned model. A CKA of 1 basically means perfect similarity. A CKA of 0 basically means no similarity at all. Okay. In fact, CKA of X and Y, two matrices X and Y, is calculated as follows. It depends on this function called as HSIC of KL and divided by square root of HSIC KK and HSIC LL, where K and L are essentially XX transpose and YY transpose. Okay. So we'll of course understand what these X and Y are, but the whole point is that once you have two matrices X and Y, which are sort of representations, hidden state layer-wise representations of pre-trained model, and Y is hidden state representations, layer-wise pre-trained representation, hidden state layer-wise representations of fine-tuned model. Okay. So you do XX transpose, YY transpose, you get K and L, and you do this computation, and that gives you the CK value. Again, CK value of 1 basically means good similarity, right? So what is this HSIC guy? Well, it's basically Hilbert-Schmidt independence criteria values, right? So that's that. So how do you get this matrix X and Y? So you essentially, when you have text input, each of those words in the text input, you get their semantic representations, whether it is BERT or GPT-2 or T5 encoder, right? You get like a 768 dimensional representation per token. You take all the tokens for a particular sentence, average them out, and that gives you a 768 size representation for each sentence. So in this work, we basically take those sentences and then come up with a matrix. So essentially, if let's say the input contained 100 sentences, then you would have a matrix of size 100 cross 768. If it had like 10 sentences, you would have a matrix of 10 cross 768. Okay. So that's basically, so if you take those representations from the pre-trained model, that is your X. If you take representations from your fine-tuned model, that is your Y. And that's how CK is computed. Okay. Now, on the other hand, there is another metric called as STIR. Now, and again, these metrics are not something that we have defined. These are popular in the NLP literature recently. Okay. So what is STIR? So how is STIR computed, and what does it capture? Okay. So STIR is defined as follows. So given, let's say a pre-trained model M1, okay, and a fine-tuned model M2, okay, and n different data samples. So if you have n different data samples, your pre-trained model M1, your pre-trained, your fine-tuned model M2, STIR sort of defines how invariant M2 is to perturbations of the samples that are imperceptible by M1. So basically, you essentially have these n data samples, you try to perturb them slightly such that M1 does not see those perturbations. M1's outputs don't change at all. The pre-trained model's output don't change at all, right? So in those cases, how much do the outputs of the fine-tuned model change? Of course, if they change a lot, that basically means that the fine-tuned model is sort of very different from the pre-trained model. If they don't change too much, it sort of just means that the fine-tuned and the pre-trained model representations are pretty similar. Okay. So now to be able to compute STIR in our case, again, STIR can be computed the way I mentioned. STIR basically is defined as fine-tuned given pre-trained. But of course, you can also compute the other way around. So you can also compute STIR of pre-trained given fine-tuned. Okay. Now the way this is done is that you take the data set, you take half of the data set, 20 times. So you sort of sample half of the data set 20 times. So if you had like in the original data set 10,000 examples, well, you sample 5,000 examples and you sample it 20 times. So every time there is a chance that you will get a very different subset, right? So and then you obtain X dash, this small data set out of X, where X dash are examples with the smallest L2 norm with respect to M1. Okay. So you essentially remember M1 is your pre-trained model. So you make small changes in your original input and you basically see if those cause any changes in the pre-trained model's output. Those, of course, there'll be some changes in the output of the pre-trained model. Now you essentially take those samples for which these changes are minimum. So for these changes are minimum. Okay. So that's basically how you essentially get those samples for which they are imperceptible or very small changes in the pre-trained model, and then you try to see how much of the change happens in the fine-tuned model. Okay. So, and as I said, STIR can also be computed in the other way around, pre-trained given fine-tuned. So you could basically sample, smallest L2 kind of examples from the fine-tuned model, and then look at the changes that happened in the pre-trained model. Okay. So given these two models, M1 and M2, STIR is computed as follows. You basically have the input data X, and it's basically computed as a CKA between the fine-tuned model's representations for X and the fine-tuned model's representation for X dash. Yeah. And of course, you basically average it over all those examples in the X dash. All those 20 X dashes. So remember, you obtain like 20 different X dashes by sampling the data 20 times. So you take the average across all of those 20 different data sets. Remember, there's no M1 here because M1 has already been used just to derive X dash by itself. Yeah, that's how it's a function of M1 and M2, specifically M2 conditional on M1. Okay. So in this work, we basically explore several kinds of text perturbations. So we explore these ones. So we drop all the nouns or all the verbs in the input. Now, again, they are done separately. So the first perturbation is drop all the nouns. Second perturbation, drop all the verbs. Third perturbation, drop all the first word in the sentence or in the input, right? Fourth perturbation, drop the last word. Fifth one is swapping text. So swap one or more words with one or more other words, right? The next one is changing characters. So change one or more characters in a word by a randomly chosen character with a probability of 10. So 0.1, that is 10% of the characters, you basically try to perturb by replacing them with some random character. Okay. Add text. So essentially append irrelevant words to the text, approximately 10% of the existing words. So how much? So essentially, you don't add too much of noise, just add 10% of the existing number of words. Bias perturbation, so switch the gender of one or more words, switch the gender of one or more words, and that is how you introduce bias. Okay. So those are the text perturbations that we experiment with. Of course, we also experiment with several NLP tasks. So these models have been fine-tuned for these for generative tasks as well as classification-based tasks. So of course, you can't do generation using BERT. So therefore, for generative tasks, we only experiment with GPT-2 and T5 base. For classification tasks, we experiment with BERT-based GPT-2 decoder, and then for T5, basically use the encoder. Okay, for classification tasks. Now, classification tasks basically include the tasks from the glue benchmark. So all the nine different tasks. So two of them are single sentence tasks, the corpus of linguistic acceptability, and then sentiment analysis task. Then 3 of them are essentially similarity and paraphrase tasks. This is basically Microsoft Research Paraphrase Corpus. And then you have semantic textual similarity and Quora question pairs, right? And then, we also experiment with the inference tasks, specifically, essentially different variants of the natural language inference or textual entailment tasks. Okay. For generative tasks, we basically consider 3 different tasks, one data set per task. So essentially, we have text summarization, free form, text generation, and question generation. Now, each of these tasks have their own specific metrics. So, there are different kinds of metrics. There is, for example, there could be simple classification accuracy kind of metrics, or there could be Rouge kind of a metric for generative tasks and so on. Okay, so if you consider metric M, and let's say on the clean set, a model scores MC as the metric value. On the perturb set, if the model scores MP as the metric value, then we find robustness using this. And this is sort of obvious as a robustness definition, right? So, so if you perturb the data set, well, you typically expect the accuracy to reduce. So therefore, MC minus MP is the reduction in accuracy, and MC is the original accuracy. So this basically just says that, hey, if there was a reduction, how much was a reduction? And 1 minus of that reduction is robustness, right? So typically you expect your model to have a robustness of 100% or 1, basically saying it's very robust model, even if you perturb, nothing changes, right? A model which is very, very dumb or very, very, sensitive has a basically robustness of 0. Of course, you want your models to be as close to 1 as possible. So what do our experiments show? What do we observe, right? So let's start with the first experiment, fine-tuned versus pre-trained models. So how does fine-tuning modify the layer representations for different models, okay, across different tasks? So what you see on the right side is basically results for the 9 glue tasks. So they are, all the 9 tasks being shown there, okay? And what you also see is that for every task, we basically have a curve for BERT, GPT2, and T5. So therefore, there are 3 colors. And then there are also curves for CKA versus STIR. Okay, there are curves for CKA versus STIR. So on the y-axis, therefore, we are plotting CKA versus STIR. On the x-axis, we have layer depth. So remember, all of these models are basically base kind of models. So T5 encoder is also 12 layers. BERT is 12 layers, and GPT2 is 12 layers. Okay. So therefore, on the x-axis, you see 0 to 11. So that's basically that. And what you also see, so basically, yes, of course, you see 0 to 12, 0 being the embedding layer, and then 12 being the 12 layers, essentially. Okay. So what are the observations from these plots? Okay. So the main observation from this plot is that GPT-2 had fewer affected layers, indicating higher semantic stability. Okay. So as you observe, GPT-2 is the green curves, is a set of green curves. And what you observe is that typically GPT-2 has fewer affected layers. So for, let's say, for example, this one, you see for the first 11 layers, hardly there is any impact of perturbation on GPT-2. Okay. Or rather, hardly there is any impact of fine-tuned versus pre-trained models, specifically for GPT-2, right? So that's that. Now, CK values for GPT-2 remained mostly higher than those for BERT. So if you basically look at GPT-2, the CK values, so if you look at it, CK values typically for BERT remained mostly higher than those for BERT. Okay. Just says that, yes, I mean, when you are fine-tuning GPT-2, there is not much changes that happen, or rather lesser changes happen for GPT-2 compared to BERT. Okay. CKA or STIR sort of drop from the initial to the later layers, which basically means that when you're fine-tuning a model, of course, as expected, fine-tuning impacts the later layers more. Okay. And now, of course, what is also expected, what is also seen is that if you just take representations from one layer, from any of these layers, and compute the accuracy, you of course observe that the accuracy of the final layers of the later layers is much higher. Okay. So what is observed is that accuracy increases as you go from initial to later layers, but CK and STIR drop, which basically means that the fine-tuning impacts later layers more. And also it means that CK or STIR sort of are inversely proportional to accuracy with respect to layers as you vary the layers. Okay. Now, lastly, you observe that CK and STIR vary consistently across all the 3 models. So this consistency sort of implies that these data characteristics of the particular task that we have experimented with are better captured by the pre-trained representations. Okay. This also explains why transfer learning using these models is so successful in NLP as we know today. Okay. That's that. Now let's go to the other question about robustness. So how robust are these classification models to perturbations in the input text. Okay, so remember we have done these various kinds of perturbations and we have experimented with these different models over various classification tasks. Okay, so on the y-axis, what is plotted is the robustness score. Okay, is the robustness score. So of course, we've plotted here robustness scores for BERT, GPT2 and T5, all three of those. Okay. So there are some very interesting observations here. So the most important observation is that change character has the has the lowest impact in terms of robustness. So in the sense, or rather, so has the most impact in terms of robustness. So if you change characters, that basically impacts robustness the most. While on the other hand, including gender bias does not change anything much in terms of classification accuracy. So the most impact is caused by these kinds of things, changing characters, dropping nouns, and dropping verbs, and making gender bias kind of changes essentially has the lowest impact. Also, what can be observed is that the green curve stays at the top, which basically means that GPT-2 is the most robust model, while the red curve stays at the bottom, which basically means that the BERT it has lowest robustness in that senses. So, which basically, implies that GPT-2 may be better suited when the input text is noisy or incomplete, so as to ensure good accuracy of the models across these tasks. Now, the next question to answer is the impact of input text perturbations on fine-tuned models task dependent. So, when you so in the previous plot that we observed, we did not really care about tasks. We have sort of averaged these scores across tasks. But now if you look at these tasks and you look at across the models, how do these text perturbations impact the task accuracies for specific tasks for these fine-tuned models, right? So what you see here is, at the top you have these, on the rows you have these perturbations, and overall you have these 5 tasks and 4 tasks, total all the 9 classification tasks for which you see the results here. Okay. So what do we observe here? So what is basically shown also, right? So in every basically for every task, there is also a metric that you see here, Matthews correlation coefficient for COLA, accuracy for SST2, and so on. And for every task, you have results shown for the 3 models, BERT, GPT2, and T5. Okay. And these are basically robustness score values, So these are basically robustness score values with respect to that metric. So this is not the Matthews correlation coefficient. This is robustness scores. Remember, okay. And in every row, the highest robustness score is highlighted. So 0.24 is the highest robustness that you obtain using T5 if you drop nouns. Okay. So and then in every column, the top and in every column, the lowest 3 robustness scores are highlighted. In every column, the lowest 3 robustness scores are highlighted by an underline. Okay. So what do you observe across these results? First of all, you observe that if you look at a single sentence tasks like COLA and sentiment analysis, you observe that GPT-2 typically is super robust, right? So you see a lot of bolds in this area, right? Especially for COLA. Now, if you look at sentiment analysis, you observe that, well, BERT is, quite robust with respect to certain perturbations, but for other perturbations, GPT-2 is robust in that senses. Okay. So in sentiment analysis, in fact, in sentiment analysis, you sort of observe that the numbers are reasonably much higher, right? So, 0.92, 0.95, 0.98, and so on. So you observe that all models are sort of very robust, except for change character. If you look at change character, that's basically 0.84, 86, and 884, and so on. So, and this correlates with our observation on the previous slide that change character is very difficult as a perturbation. So change character is a perturbation that causes these models to give really bad results across different tasks. Okay. Now, if you talk about similarity and paraphrase kind of tasks here that you see them, for MRPC, GPT-2 is the best and most robust model. For STSB, you basically observe that BERT is the best, and for QQP, you sort of have mixed results across these models. Okay. If you look at NLI kind of tasks that you see here, you observe that GPT-2 is better for RTE. Specifically for RTE, you observe that GPT-2 is really good, but in general, GPT-2 performs reasonably well across different tasks, except for WLLI, where GPT-2 performs well for certain. In general, well, even in WLLI, right? I mean, these scores are very close to 1, basically saying that GPT-2 performs reasonably well across all of the NLI tasks as well. Okay. So in conclusion, we observe from these results that transform models demonstrate high tolerance towards dropping first word and bias perturbations. However, they are not as tolerant towards changing characters or dropping nouns and verbs. Okay. Impact of text perturbations on fine-tuned models is surely task dependent. So we do observe that for certain tasks, there is not much of an impact. For example, for WNLI, robustness is super high. Also for SST2, robustness is super high, but for some other tasks, robustness actually drops significantly. For example, for the COLA task, you observe these particular values, they are pretty low in that senses. Okay, so yes, the impact is task dependent. Okay. Now, if I talk about generative tasks, you can talk about these kinds of impact for generative tasks as well. And the results are pretty similar. Of course, for generative tasks, we just compare for GPT-2 and T5. And you observe in general that yes, GPT-2 is more robust across different metrics and across different tasks. But you do have similar kind of observations that in general, changing character, dropping nouns, dropping verbs have most of these underlines, which basically means that dropping nouns, verbs, or changing characters have the highest impact in terms of robustness. Okay. Now, the last question that we wanted to sort of ask is the impact of perturbations on fine-tuned models different across layers. Okay. So if you so for this experiment, what we did was to take take the model representations with the clean data and take the representations from different layers and try to compute the accuracy for each of those tasks. Right. And then we also perturbed the input data and then trained the models. And then, we looked at each of those layers and tried to look at the accuracy per layer. Okay. And then we tried to figure out which are the top 3 layers for which the change was the maximum, right? Which are the top 3 layers where the change was the maximum. So these top 3 layers are the ones that are plotted in different colors that you see here. Okay. So essentially, you see the orange color, the green color, and the blue color. Well, these colors basically represent the most affected layer, the second most affected layer, and the third most affected layer, blue, green, orange. Okay? And these particular charts are actually shown for the BERT model. Of course, the charts for GPT-2 and T5 are there in the paper. You can have a look at them later. Okay. There is a chart per perturbation. So for every perturbation, you will have the most affected layers being different from the other perturbations. Okay. So what are the observations? And of course, what does the radial stuff mean? Radial stuff means 0 to the 12th layer. So where 0 is the embedding layer and up to 12 if you go, that basically represents from initial to later layers in that senses. Okay, what are the observations? So the observations are that the most important changes happen in the initial and last layers. Okay, if you observe, these are top 3 plotted. So if you observe, for most of the tasks, of course, we've also plotted various tasks here, right? So various tasks have also been plotted here. So what you observe is that most of the changes either happen near the later layers or near the initial layers. Very few changes you'll observe in the middle layers. So if you really, look at the 4th, 5th, 6th, 7th, 8th, 9th layer, very few tasks, have changes in those layers. Okay. So that's that. Initial and last layers are most sensitive to these perturbations. And also add text affects the lower layers. So, if you look at add text kind of perturbation, very clearly across different tasks, you observe a whole bunch of perturbations happening only in the lower layers. And this sort of makes sense because if you're adding text, adding text to the original input, 10% extra text, unrelated text, that has a lot of impact in the initial few layers. And that sort of is also captured in this analysis that we did. Okay. Now, although those charts are not shown here for other models in this video, we found that a whole bunch of these observations are very similar across models. The layers which are most affected by these text perturbations tend to be consistent across different models when you vary when you look at them across different tasks, okay, and different perturbations. So which basically implies that all of these models basically capture certain shared linguistic features and contextual information, and those particular characteristics that these models capture are important across these models. Okay. However, there are variations across tasks. So we observe that for BERT, later layers are more impacted. So typically we observe that for the BERT model, later layers are more impacted due to these perturbations. For GPT-2, however, we observe that initial layers are more impacted typically, right? And so that's the trend that we observe. And for T5, we do observe that typically initial layers are mostly impacted, but also some middle layers are also affected. Okay. So that's the observation across these models. Okay. Lastly, amongst all of these perturbations, swap text is an interesting perturbation. It tends to affect multiple layers across different models. So, in general, we observe that typically the initial layers or the later layers are impacted. But for swap text perturbation, we did observe that multiple layers across, across different models are impacted. This sort of says that contextual information so the context changes a lot when you swap the text. So this implies that contextual information is distributed and integrated throughout the layers of these models. So if you do the swap text kind of a perturbation, you observe that robustness changes happen across different layers in these models, in various models. Okay. So let me conclude this video. So we did experiments to check what changes in BERT, GPT-2 and T5 when you do fine tuning with respect to the pre-trained model. So fine tune versus pre-trained model, we observe that the last layers of the models are most affected than the initial layers while fine tuning. Okay. Then we also did robustness analysis with respect to several text perturbations, and we observed that GPT-2 exhibits more robust representations compared to BERT and T5, which basically means that if you have a chance of a lot of noisy input, GPT-2 can give you way more better results compared to BERT and T5. Talk about OCR outputs, maybe GPT-2 performs better on those kinds of outputs rather than BERT or T5. Okay. Models are seen to be most affected by perturbations like dropping nouns, changing characters, dropping verbs, and least affected by perturbations like changing the gender or adding bias because of changing gender of certain words. Okay. Certain layers are consistently impacted across different models, indicating the importance of specific linguistic features and contextual information that is relevant across different NLP tasks and across different models. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.